Yeah, thank you for the nice introduction. My pleasure to speak here at this lovely conference, and tonight I will show you some of our results and strategies towards sustainable fabrication of perovskite PV modules. I will start quickly with the very basics. You probably all know that materials with this perovskite crystal structure, which is depicted here, give us access to a range of very efficient photoabsorbers, which can enable power conversion efficiencies of thin film perovskite solar cells with an efficiency up to 27% for single junction devices, and also above 30% now for all perovskite tandem devices. What is sometimes a bit overlooked, but also very important to mention, is that the module efficiencies are also going up and catching up to the cell results. We've also seen this very nicely in some company presentations yesterday and today. And since this year in this annual chart, we can also find the first data point for all perovskite tandem modules with an efficiency of 22.8%, which really highlights the readiness of this technology efficiency-wise. So this is the information which you can easily find. It gets a bit more complicated when you want to understand how these devices are actually built. And on this 27% device, there's no information given actually. So the next best guess is that we take a look into literature, where we find, for example, a 26.3% efficiency device, where all process information, etc. are given. And if we analyze this a bit closer, I highlighted this in red, we find some things which are a bit of a concern to me, because it's a very small area. You have cesium-containing perovskite, you have noble or scarce metals in the device stack, non-scalable processes, typically for the very high efficient devices, they also made by spin coating, and also toxic solvents, like here the DMF, and also halogenated antisolvents, which make it even worse. And this is an issue, I believe, and a former colleague of mine, Lukas Wagner, who is now at the University of Marburg, came up a couple of years ago with this graph here, where we calculated the material demand for an assumed 1 terawatt peak production of perovskite PV and related to today's mineral production, so what is currently being mined. And again, this was done for different, this was done for several categories, like contact layers, perovskite themselves, interconnection layers, and you can find, well, of course, that noble metals like gold are a no-go. They are just too scarce, and also, of course, very cost expensive, so you cannot use these for opaque electrodes. And, of course, indium is sometimes an issue. What was a bit surprising is that also cesium can be an issue if you work with cesium-containing perovskites. This is not because we have so little cesium in the world, there's enough of it, but it's just a matter of how much is currently being produced or mined, which could lead to material criticality issues. And at the same time, some of the metal back electrodes, which are typically applied in the layer stacks, are associated with degradation mechanisms. So, for example, you can find gold migration throughout the layer stack, leading to detrimental device performance over time. And also some degradation mechanisms are related to the presence of silver and silver iodide being formed when you have this as a counter electrode. And this was our starting point, a bit where we thought how we increase the sustainable fabrication of perovskite PV. And this list might not be complete, but our approaches are we want to make sure that we can, in principle, fabricate these devices with a low environmental impact, which means we want to apply low temperature processes and low emissions during the fabrication. And our approaches here are scalable coating processes with green solvents and printing of back electrodes, not evaporation of metal electrodes. And secondly, the low material criticality, which we want to address, where we want to replace obviously high impact materials. For example, we want to avoid cesium in our perovskite absorbers, and we want to replace noble metal back electrodes. And some results on this I will show you in the next couple of minutes. Starting with green solvents, we chose to work with green solvent processing of a cesium-free perovskite, FAPBi3. And we chose to use gamma-valerolactone as a solvent for that, GVL. This is nothing new, but it's a very green solvent, as green as can be, because it's also bio-based. You can, in a few synthetic steps, synthesize this solvent from biomass or fructose. And when we started to work on this, we found that the maximum concentration of the precursor materials we use is significantly lower than in typical solvents like DMF and DMSO. And then we, of course, started thinking how can we increase it to have the same layer thickness and so on. And, of course, one logical thing or first thing which you could think about is heating the solution. This, however, did not lead to any result that we expected, because instead of increasing the solubility, we found a precipitation of a black material, and of course this black material turned out to be the perovskite, which was analyzed by XRD. And we could find that we really have this inverse